Hi and welcome to this tutorial on the properties of metallic bonding. So in the previous tutorial we had a look at covalent bonding, covalent structures, so simple covalent structures or simple molecular structures versus giant covalent structures. And we also discussed the physical properties, the differences in the physical properties. In this tutorial we're going to have a look at metallic bonding and of course the physical properties of metallic bonding as well. So with metallic bonding we are going to have our central metallic ion and then a sea of delocalized electrons. And they're nice, they're in blue, so that makes that easier to think about, the sea of delocalized electrons. Now, delocalized electrons are electrons that are not associated with a single atom or a covalent bond. They're able to freely move around the structure. And metals have lots of delocalized electrons, so that's why we call them a sea. Most metals are going to be found in groups 1, 2 and 3 of the periodic table. So they have either 1 electron, 2 electrons or 3 electrons in their outer shell, depending on their group. And each metal atom is going to lose electrons in order to form an ion. Because you can imagine it's much easier if you're in group 1 to lose 1 electron to get the full outer shell, the shell below, than it is to gain 7 electrons to get the full outer shell of that shell. And the same for group 2 and group 3. So they're all going to be losing and forming positive cations. So let's have a look at our example here. So on the left, we've got the electrons are lost by the metal atom in the center, and they become delocalized into the sea of negative charge around the outside. And on the right, we've got another example. So we've got the positive metal ion. It's going to form when the metal atom loses its electrons. So sodium, solid sodium metal is going to be its sodium plus in the center, and it's going to drop off its electron into sea of delocalized charge, and calcium is going to drop 2 electrons off into that sea of delocalized electrons. So when we think about the bonding, metallic bonding is the attraction, the electrostatic attraction between the positive ions and the surrounding delocalized electrons. Okay, so it's effectively all these attractions that are happening here that is causing the metallic bonding. So like I said, the positive metal ions and their delocalized electrons are packed closely together in a regular arrangement, hence why they're solid. And the figure below, so this ion here represents an example of metallic bonding between our positive ions and the electrons. Something that students do slip up on quite a lot here is that they are ions. Sounds similar, but you need to use both words to discuss these. You cannot just refer to this as ions with a sea of delocalized electrons. It's ions. So it can be a bit confusing. When we think about the strength of metallic bonding, we need to be able to compare the strengths of the different metals in the periodic table. And it depends on the size of the positive charge. So is it in group 1, 2 or 3? Does it form 1 plus, 2 plus or 3 plus ions? The size of the metal ion in terms of the radius, how large, how many shells does it have, and the number of mobile electrons per atom. So if we're in group 3, then we're going to be dropping 3 electrons off into the sea, as opposed to just 1 for group 1. So when we're thinking about the arrangement, so the arrangement of those ions and the electrons and how closely they're packed together, for example, that is going to determine the melting and boiling points, the electrical conductivity, and the solubility. So there's quite a lot of physical properties to consider. So if we're thinking about melting and boiling point, this is dictated by the strong attraction between the metal ions and the delocalized electrons. So with all metals, it's a high melting boiling point, because those electrostatic forces of attraction are strong. The more delocalized electrons present, the higher the melting and boiling point, the stronger that electrostatic force of attraction is holding everything together, the more energy required to break it down and melt it. So calcium is dropping 2 electrons off. Each atom is going to drop 2 electrons off into the sea of delocalized electrons. So it's going to have a higher melting and boiling point than sodium that's only dropping 1 electron off because it's in group 1. Then we've got to think about electrical conductivity. So they are both electrical and thermal conductors because they've got delocalized electrons that are able to freely move around and carry a current, a charge, and they can transfer kinetic energy between themselves. So that's why metals can conduct electricity. And then solubility. We know this, and you should know this just from watching the world around you. Metals are insoluble in solvents. These strong metallic bonds, those electrostatic forces of attraction, are much stronger than the forces between the metal and the solvent. So the attractions will keep, they won't break, they're not interested in the solvent in terms of stability. And the exception, though, is liquid metals.